Okay, in today's lecture, we're going to cover the last bit of the section 6.6 material on surface integrals. So in the last part of this section, we had defined a surface integral of a vector field, also called flux of that vector field across a surface. And we were only considering the case where our surface S was the graph of a function of two variables. But of course, we've seen throughout this section that not all surfaces can be considered as the graph of a function, but some surfaces are described by parametric equations. So in the last part of this section, we will talk about how to define a flux integral over parametric surfaces. So let's suppose that we have a surface S, which is a parametric surface, and it's defined by the vector function r of uv, where the parameters uv lie in some plane region D. Then our surface integral of the vector field over the surface S, also called the flux of that vector field across the surface, is evaluated by converting this to a double integral over the parameter domain D. And the function that we're integrating is our vector field F evaluated at r of u and v. So for our vector function r of uv, we have component functions for x, y, and z in terms of u and v. So we're going to replace x, y, and z in the components of our vector field by these functions of u and v. And then we will take the dot product of that vector field in terms of u and v with the cross product of the partial derivatives of the vector r with respect to u and v, and then evaluate this double integral with respect to area over that parameter domain. So we've seen throughout this section that that cross product of these partial derivatives is considered as a differential of surface area for a parametric surface. So in this next example, we are asked to find the outward flux of the vector field zyx across the sphere centered at the origin of radius 1. So we know one way that we could approach this is to consider the upper and lower hemispheres for this sphere as the graphs of a function of x and y, and then evaluate the flux over those upper and lower hemispheres individually and take the sum. But that gets a bit tedious here. So instead, we could look at finding a parametric representation of this sphere and then making use of our new formula for flux in terms of a parametric surface. So in this example, since our surface is a sphere, we might use spherical coordinates to parameterize this. So let's say in this example here, we could parameterize our surface S as a vector function, r, in terms of spherical coordinates, rho, gamma, or rho, phi, and theta. And since we have a sphere of constant radius 1, our rho value will be 1 throughout. So here, our vector function will just depend on the phi and theta coordinates in terms of the spherical coordinate system. So our x component in terms of spherical coordinates is rho, which is 1 here, times sine of phi, times cosine theta. Our y-coordinate in spherical coordinates is given by rho, which again is 1, times sine of phi, sine of theta. And our z-coordinate is given by rho, which again is 1, times cosine of phi. And here, if we're talking about the entire sphere, we would have a range of our parameters where theta would range from 0 to 2 pi to get a full rotation around our sphere in the xy plane. And then our phi value could range from 0 to pi. Since we're talking about the full sphere, we could revolve from the positive x-axis, positive z-axis, all the way to the negative z-axis, which would correspond to a range of phi values from 0 to pi. Now, once we have this parametric representation of our surface, we need to evaluate the function, or the vector field, f, in terms of u and v. So let's look at what we have here. If we're looking at the vector field f, defined in terms of our parameters, phi and theta, well, the first component of our vector field was z. And here the z component of our parametric surface is given by cosine of phi. Our second component of the field was y, and our y component for our parametric surface is given by sine of phi times sine of theta. And then our last component is x, and our x coordinate for this surface is given by sine of phi cosine theta. So we found our function, or our vector field, in terms of the parameters phi and theta. And now we still need to calculate the partial derivatives of this parametric representation for my surface with respect to phi and theta, and then take the cross product of those partial derivatives. So let's look at what we have for our partial derivatives. Here, the partial of r with respect to phi would be cosine of phi cosine theta for our first component. The second component, we would have cosine of phi sine of theta. And our last component would be negative sine phi. And the partial derivative of r with respect to theta would have a first component of negative sine phi sine theta, sine phi cosine theta, and 0. So we need to find the cross product of those vectors, which are our partial derivatives. So looking at r phi cross r theta, we're taking the determinant of a 3x3 matrix where our first row consists of standard basis vectors I, j, k. Our second row consists of the components of r sub phi, which were cosine phi cosine theta, cosine phi sine theta, and negative sine phi. And our last row is the partial derivative of r with respect to theta, so we had negative sine phi sine theta, sine phi cosine theta, and 0. So taking this cross product, let's see what we get. Our first component, that is our I component, would be 0 minus a negative, so plus sine squared phi cosine theta. Our J component would be sine squared phi sine of theta minus 0. So here, sine squared phi sine of theta. And our K component, we have sine phi cosine phi times cosine squared theta minus a negative, so plus cosine phi sine phi times sine squared theta. So since sine squared theta plus our cosine squared theta is equal to 1, we're left with sine phi times cosine phi. For that last component. So finally, we're ready to set up our integral for flux. So here the flux, which would be the double integral, or excuse me, the surface integral of our vector field F over the surface S, is then evaluated as the double integral over our parameter domain D of the dot product of our vector field F in terms of u and v with this cross product that we just found. So recall that we found our vector function F in terms of the parameters phi and beta was given here, and our cross product was just found here. So let's see what we get for our integrand. So taking the dot product, we have cosine of phi times sine squared theta, or sine squared phi cosine theta. So we start with a sine squared phi cosine theta plus, for the product of our second components, we have sine phi sine theta times sine squared phi sine theta. So altogether we have a sine cubed phi sine squared theta. And then plus, for our last component, we have sine of phi cosine of theta times sine of phi cosine of phi. So on the end, we are left with sine squared phi cosine phi times cosine theta, integrating with respect to area there. So here, setting this up as an iterated integral, we have, let's make our outer integral with respect to phi, and we had seen in our earlier work that the range of values for phi were from 0 to pi. So our outer integral would range from 0 to pi. Our inner integral with respect to theta would range from 0 to 2 pi. And now let's look at our integrand. So combining some like terms, let's see where we have like terms. Our first term, sine squared phi cosine theta. In our last term, sine squared phi cosine theta are the same. So we have together 2 times sine squared phi cosine theta plus our sine cubed phi sine squared theta, integrating in the order d theta d phi here. So to find this, or to evaluate this iterated integral, we're first integrating with respect to theta. So this first term, which just involves a cosine of theta, is easy to evaluate. What's a little trickier here is the sine squared theta. So we've got to make use of the fact that sine squared is equal to 1 minus cosine of 2 theta all over 2. And evaluating this antiderivative, we have the integral from 0 to pi of 2 sine squared phi cosine phi, and then the antiderivative of this cosine theta term is then sine theta, plus sine cubed phi times the antiderivative of our 1 minus cosine of 2 theta over 2 with respect to theta is theta over 2 minus 1/4 sine of 2 theta. We're evaluating then from theta equals 0 to 2 pi, and then integrating with respect to phi. So when we evaluate at theta equals 2 pi, everywhere that we had a sine of theta, or sine of 2 theta, these values become 0. and we're left with this theta divided by 2, so 2 pi over 2, or just pi for that term. So we have the integral from 0 to pi of 2 sine squared phi cosine phi times 0 here. So this first term disappears, plus our sine cubed phi times our 2 pi over 2 leaves us with a constant of pi out in front. And then when we evaluate at theta equals 0, well, sine of 0 is 0. Sine of 0 is again 0, and we have 0 over 2, which is 0. So we're left with only this pi times sine cubed of phi d phi. So to integrate an odd power of sine, we can factor out, I'll pull my constant pi out in front, and to integrate a odd power of sine, I'm going to factor out one of the powers of sine. So I'll change this into a sine squared phi times sine of phi d phi. And then I'm going to use the fact that sine squared is the same as 1 minus cosine squared. So my sine squared of phi I will rewrite as 1 minus cosine squared of phi, and then I've got this sine phi d phi on the end. So to find an antiderivative, I can make use of a u substitution. So if I were to let u equal cosine of phi, then du would be negative sine of phi d phi. So converting this to an integral in terms of u, we have our constant pi out in front. We have the integral of 1 minus u squared. Now our sine of phi d phi on the end is the same as negative du. So I'll pull my constant negative out in front with the pi. And then let's see what we have for our new limits of integration. So when phi is 0, u is cosine of 0, which is 1. And when phi is equal to pi, u is cosine of pi, or negative 1. Now here, if I wanted to reverse the order for these limits of integration, I could get rid of this extra constant negative 1 that we had out in front of our integral. So if I change the sign back to a positive pi, then I can switch my limits of integration from negative 1 to positive 1. And we've got our 1 minus u squared du. So for an antiderivative, we have pi times u minus u cubed over 3, evaluated from negative 1 to positive 1. So that gives us pi times, when we plug in 1 for u, we have 1 minus 1/3, or 2/3. Minus, when we plug in negative 1, we have negative 1 plus 1/3, so subtracting a negative 2/3. And so altogether we are left with 4/3 pi, or 4 pi over 3, for the flux of that vector field across this unit sphere. Okay, so here, of course, notationally, this is pretty tedious, making use of the spherical coordinates, but this is still an easier approach than if we were to try to calculate the flux by considering the upper and lower hemispheres individually. So to finish out this section, we'll consider one application of flux here. So there are several applications which are discussed in much more detail in physics and engineering courses, but one that we'll discuss here is heat flow. So let's define heat flow formally. So here, let's suppose that we have the temperature in some object, at any point, x, y, z, is given by a function, capital T of x, y, and z. So we have some object in space which has varying temperature throughout, defined by some function T. Then the heat flow of the vector field, or the heat flow is defined as this vector field, F, which is given by negative K times the gradient of our temperature function, where K here is some constant called the conductivity of our substance, whatever this object is made of. So if we're interested in determining the rate of heat flow across some surface S in a body made out of a given material, then we would evaluate our flux integral. We want to know what is the rate of heat flow across the surface of this body. So as an example of this, let's consider the following. Suppose that the temperature at some point x, y, z in a substance with a known conductivity of K equals 6.5 is given by 2 times x squared plus y squared. Then we want to find the rate of heat flow inward across the cylindrical surface x squared plus y squared equals 6 for z between 0 and 4. So before we jump into this problem, let's think about the surface that we're considering the flow across. So here we were told that we're looking at a cylindrical surface given by x squared plus y squared equals 6. So that is a cylinder centered along the z-axis, since our z variable is missing. And the cross-sections are circles of radius square root of 6. And the values of z are being bounded by 0 and 4. So we have a cylinder that looks like this, where our radius, r, is the square root of 6, and our height would be 4 here. Our bottom part of this cylinder is in the xy plane, z equals 0, and the top of our cylinder lies in the plane z equals 4. So we're determining for this surface what would be the inward heat flow across this surface if it is submerged in, or if the temperature at any point x, y, z in this substance in which it's submerged is given by the temperature function. So our first step here is to find the vector field F that we're working with that describes our heat flow. So it's given by negative K times the gradient of our temperature function. So let's start by finding this. So here I will say first our vector field F, which is a field in x, y, and z, is given by negative K. So here negative 6.5, since our conductivity was given as 6.5, times the gradient of our temperature function. So here the gradient of this temperature function, 2 times x squared plus y squared, would be 4x for partial with respect to x, 4y for partial with respect to y, and 0 for the partial with respect to z. So this simplifies to, if we distribute our negative 6.5, we have negative 26x, negative 26y, and 0. Now, in order to find the rate of heat flow across this surface, we want to evaluate the flux of this vector field over this surface. Let's call it S. Now this surface, part of a cylinder, is a little difficult to describe in terms of rectangular coordinates So instead, we could make use of cylindrical coordinates. We might suspect cylindrical since we're defining part of a cylinder. So let's say now our surface S is given by the vector function, let's say in cylindrical coordinates, r of the parameters theta and z, where the x-coordinate in terms of cylindrical coordinates is given by r. In this case, the radius of our cylinder is a fixed square root of 6 times cosine theta. Y is given by r, which is root 6 sine of theta. And z in cylindrical coordinates is just given by z. And here the range of our parameter values would be where theta ranges from 0 to 2 pi, since we're talking about a full revolution around our cylinder. And z would range from 0 to 4. Since our bottom part of the cylinder lied in the xy plane and the upper part in the plane z equals 4. So now, to evaluate the flux integral for a parametric surface, we need to evaluate our vector field f in terms of the parameters, here theta and z. So our first component for this vector field was negative 26 times x, and the x component for points on our surface is given by root 6 times cosine theta. So here we have negative 26 root 6 cosine theta. Our second component for the field was negative 26y, but for points on the cylinder, y is given by root 6 sine theta. So we have negative 26 root 6 sine theta. And then our z component is always 0 for that field. So here we have 0. Now we also need to calculate the partial derivatives of our vector function r of phi and z, of theta and z, with respect to theta and z. So let's look first at r sub theta. So our first component, differentiated with respect to theta, is negative root 6 sine theta. The second component would be root 6 cosine theta. And our last component would be 0. And the partial derivative of r with respect to z is given by 0, 0, 1. So taking the cross product of those partial derivatives, r theta cross rz, we're taking the determinant of the 3x3 matrix, where our first row consists of the standard basis vectors I, j, k. R sub theta was negative root 6 sine theta, root 6 cosine theta, 0, and r sub z was 0, 0, 1. So for this cross product, our I component is root 6 cosine theta. Our j component is root 6 sine theta. And our k component is 0. So the flux of this heat flow across our surface S is given by the surface integral of that vector field F over the surface S. And in terms of a parametric surface, we would express this as the double integral over our parameter domain D of the dot product of our field expressed in terms of the parameters theta and z with the cross product of our partial derivatives, r theta cross rz, evaluated with respect to area. So let's see what we have here. Here, taking the cross product of these two vectors, well, we had our vector field in terms of theta and z given here, and the cross product of r theta and rz given here. So for the product of the first two factors, we have negative 26 times 6, which is negative 156 cosine squared theta. Then for the next term, we have negative 26 root 6 sine theta times root 6 sine theta. So that is negative 156 sine squared theta. And then the product of our last components, 0 and 0 is 0. So we're just left with the following. And here, these two terms are negative 156 cosine squared theta minus 156 sine squared theta reduces to a constant of negative 156. So this constant, negative 156, we can pull out in front of the double integral, and we're left with the double integral of 1 over the plane region D with respect to area. Now recall that evaluating a double integral of 1 over a plane region just gives you the area of that region. We would denote it as A of D. So the area of D here, well, let's think about what D represents. D is our parameter domain. So here we were talking about the rectangular region where theta ranges from 0 to 2 pi and z ranges from 0 to 4. So the area of that rectangular region would be 2 pi times 4, or 8 pi. So we're left with negative 156 times the area of that parameter domain, which we just said was 8 pi. So that leaves us with negative 1,248 pi. Now, one thing that we'd have to be a little bit careful of in this problem is that we were asked specifically for the heat flow inward across our surface rather than the heat flow outward. So remember that all of our formulas for flux that we've been using throughout this section rely on the fact that we're using the positive or outward orientation. So to get this inward orientation across our surface, we just have to change the sign. So here we could say the inward rate of heat flow would be a positive 1248 pi. Okay, so that finishes our section on surface integrals, section 6.6. So we saw this was quite a long section. We've defined parametric surfaces, how to find their tangent planes or surface areas, how to define a surface integral of a three-dimensional scalar function, or the surface integral of a three-dimensional vector field across a surface, also called flux, both in the cases that our surfaces are defined as the graphs of functions or by working with parametric surfaces. And as we've seen in some of these examples, these surface integrals can be pretty complicated to evaluate. So in our last two sections for Chapter 6, we'll get some nice results which make evaluating surface integrals or line integrals much easier.